All right. So this is Unit 6, COE. You don't know what COE stands for yet. Some of you might. Don't shout it out. But I'll explain it here in a second. Give it up, please. All right. Now, nope, not coefficient of energy. Close though. All right. Now we have two equations we knew yesterday. Man, I told you not to shout it out.
You told us this
Goodness.
2 days ago.
It's like we're watching a movie and you just told us the end. Hey, he
Not
dies in the end.
really.
Don't worry about it though. It's cool. All right. Back to this. So, all right. Work equals change in kinetic. Work equals the negative change in potential energy, right? These are two equations we talked about yesterday, wasn't it?
Yeah.
Okay.
Yeah.
Now, here's a roller coaster that was dragged up to the top of the first hill by some motor. Okay, some chain-driven crank. All right. I don't need what? It was Omar pulling it. So Omar somehow pulled that roller coaster car up to the top of the hill. All right. So when Omar pulled that roller coaster car up to the top of the hill, what was he working against? Gravity. All right. So Omar applied a force upward and did positive work on the car, right? What did gravity do?
6.
No, what kind of work did gravity do? It says Omar moved the roller coaster car up to the top of the hill. What kind of work did gravity do?
Many.
Negative work. Thank you, Reggie. So the force applied by gravity was downward. The displacement's up. Work did negative, or gravity did negative work. Does that make sense?
Yes, sir.
Okay. So when the roller coaster car got put up here at the top of the hill, what type of energy did it gain? Potential. Good. At part A, assuming the roller coaster has no velocity, it has only potential energy, right? Yeah. Now, that potential energy, who stored that energy? No? Jesus is in third hour. Okay. Okay, who stored that potential energy?
Omar.
Omar did the work to put the car there, right?
Why is the name Omar?
Because Omar said he pulled it up there.
Oh.
Okay? Omar, your classmate. Okay? So, Omar did the work to put the car up there, right? But he stored energy against gravity. Because when Omar put the car up there, he stored energy against gravity because gravity is going to do the work to bring the car back down. Does that make sense?
Yeah.
So, this W right here, is this the work done by Omar or the work done by gravity? Good, it's the work done by gravity. The reason why is the car, Anthony, Skylar, pay attention. The car gains potential energy when it goes up to here, right? That's a positive, right? That's an increase, isn't it? Right? But in this equation, it's a negative sign, right? So in order for this negative sign to become a positive sign, that means this work has to be negative. Which means this W right here is the work done by gravity. Okay? What about this W?
Gravity.
It's also the work done by gravity. Okay?
Wow.
Because as gravity does positive work, as the car goes downhill, gravity's doing positive work, right?
Sure it is.
Right? That positive work does what to the car's kinetic energy?
Gains it.
Increases it. Because those of you that have ridden a roller coaster before, as the car goes down the hill, what happens to the velocity?
Increases.
It increases, right? Velocity increases, that means kinetic energy increases. So down here at point B, we have some kinetic energy, don't we? Yeah. Makes your cheeks flat, Rex? Yeah. Okay. So are there any questions about that?
Is this going to be like our
It's gonna be like
problem when
last
we go
year.
to Michigan Adventures?
You could have a problem like this at Michigan Adventure.
Are we going to? Why?
Okay. So
Worst teacher ever.
now, thank you. The work done by gravity to lift the cart up to the top of this hill. Okay, guys. How does that relate to the work done by gravity to bring the car down the hill?
They're direct.
It's inversely related.
Directly
Jesus, that was
related.
the answer.
Okay. The force of gravity doesn't change, neither does the displacement. So the work done by gravity is
42.
the same. So since these two are equal, we can make this conclusion,
Oh my gosh.
right? So what this means is that as potential energy increases, kinetic energy will decrease.
I thought we
As-
already covered that.
We talked about it yesterday,
Yeah,
but just
we
making sure.
And last year.
As potential energy,
Increases, kinetic energy increases.
good, as potential energy decreases, kinetic energy.
And as I said,
Increases.
they are inversely
Alright.
related.
So,
I said
alright, at A and B, okay? At A, if our velocity is 0, right? Because usually roller coasters start by having a very small velocity start. We can assume that velocity is 0. If the velocity is 0 at A, that means all of our energy is potential, right? So that means that this is the maximum potential. Right? Does that make sense?
Yeah.
Okay. The reason why it's our maximum potential is because we said velocity is 0, which means kinetic energy is 0. Does that make sense?
What if it stops at the bottom?
The car doesn't stop at the bottom.
But what if it did?
In order for the car to stop at the bottom, that means there either has to be something in the way, which would be very tragic for the people on the roller coaster,
Well, who cares about
or the brakes have to turn on, right? If the brakes turn on, then we're taking energy out of the system.
Okay.
Okay? Just like the car slowing down in example 17 and 18. Okay?
But it would be the same thing if it was if it stopped at the
No, if we're down here
bottom.
at the bottom,
I'm talking about that.
what?
If it stopped at the top and then it stopped at the bottom.
Right, then we'd have no kinetic energy.
Yeah.
But if it stops at the bottom, then we'd have to take energy out of the system. There would be no energy left. Okay? All right. So, none. Down here at the bottom, what's the height, guys? 0. Okay? The height is 0, so that means potential energy is 0. Okay? So that means down here at B, what's the kinetic energy? No. That's maximum. Okay? The reason being, since this was the highest height, that's potential energy maximum. Does that make sense? Okay? Since this is the lowest depth, all right, that means all our potential is turned into kinetic, so this is where velocity is at its maximum. All right, does that make sense?
Yeah.
If velocity is at its highest, then kinetic energy is at its maximum. All right? Are there any questions about those two?
So someone has to do all of this just to make a roller coaster?
Well, these are all the things I think about.
Okay, so
Okay.
Very short roller coaster.
Oh, this is just a portion of the track.
But how do we know it doesn't go any lower?
What?
How do we know it doesn't go lower?
Rich. Rex?
Your picture shows it going lower than it
That was just.
Like
Yeah,
if
but-
it had water and then you touch, like,
Guys.
no, like
Hey,
it
Michael.
goes
Yeah, it goes negative.
There you go.
It's still a little bit negative.
Sure. Okay. So does that make sense, guys, about potential and kinetic energy?
Yeah.
All right. Now, change in kinetic equals negative change in potential energy. All right. Now, this equation, I know it looks like it's just kind of a second thought, but that is the most important point of what we're talking about today. Is that the change in kinetic equals the opposite of the change in potential. Meaning, as potential energy of the roller coaster decreases, kinetic energy increases, and vice versa. All right. The reason why that's so important is if I expand these deltas, so I take change in kinetic energy, and I take negative change in potential energy. If I break up those deltas, it's initial minus, or sorry, final minus initial, right? Right. So this is KE final minus KE initial, right? Okay. And this one is negative PE final minus PE initial.
Oh my goodness.
Okay. Right.
Yeah.
I broke up my deltas.
Sure did.
Okay. Now I'm going to distribute this negative sign real quick. When I distribute the negative sign, that makes the PE final negative and the PE initial positive. Right? Now, personally, I hate working with negative numbers. Okay? Because then there's all these little rules about signs and stuff like that. So I'm going to take the negative numbers out of it. So how can I make this KE initial positive? Move it over. So now it said plus. So I have plus, that means I'm moving it over. Right? How can I make this PE final positive? Move it over to the other side, right?
So you're gonna have like KE plus PE equals
So now those cancel, right?
PE.
On the left side, we have only final energies. Right? And on the right side, we have only initial energy. So now what I've shown you is that the energy we have at the end, all the energy we have at the end, right, equals all the energy we have
The beginning.
at the beginning. Okay? So what this shows by taking these two equations, these two deltas, what we're showing is that the energy we start with equals
The energy you end with.
the energy we end with.
Even if it's not as high.
We'll get to that, Rex. So ME final equals ME initial. You're probably saying ME, what's ME? Good, mechanical energy. Mechanical energy is the sum of potential and kinetic, right? Right? So, Rex, you said, even if the roller coaster doesn't get as high,
Yeah.
is that still the same case?
I was asking.
Okay, so if I'm at point A,
Yeah.
we're at maximum potential energy, right?
You sure?
We have no velocity here, right? Or very, very small.
Fine.
If I'm at point B, okay, so I can fit in Michael's world, our height is very, very small. We're not going in the ground, we're staying above, but the height is very, very small, we're going to call it 0. Okay? So that means our potential is 0, right? So our velocity, that means all of our potential turned into kinetic, right?
Yeah.
Now if I go up the top of this third hill,
Yeah.
the third hill isn't as, or sorry, the second hill isn't as high as the first hill, right?
No, it's not.
So our height is less. So how do the potential energies here compare?
Would it be?
C is less than A, right?
Yeah. Yeah.
But how is the kinetic energy at C compared to the potential or kinetic at A?
Equals.
No. How does the kinetic at C compare to the kinetic at A?
It's gotta be bigger.
More.
It's got to be bigger. It's got to be more, right? The reason why it has to be more is because all the energy we start with equals all the energy we end with.
No.
So here, all we have is potential energy. Let's say we have 100 joules of potential energy. Okay, just throwing a number out there. We have 100 joules of potential energy here, right? When we get to this spot, which is about half the height,
No, it's
Okay.
3/4.
3/4, okay, so we have 75 joules of potential energy here, right?
Yeah.
So how many joules of kinetic do we have?
25.
25. Which means that the roller coaster has some velocity at C. Okay?
But
Now you guys have all experienced this, right?
Yeah.
You go down a roller coaster, you get to the bottom here, you're going really, really fast, right?
Yeah.
As you go up to the top of the next hill, what happens to your velocity?
Decreases.
It slows down because some of your kinetic is turning back into
Potential.
potential.
No,
But the roller coaster is conserving energy the whole way.
What if you were to go right there, then go over, and then say friction increase or something, and you stop right on top of C?
Okay. Okay, you and Caleb both are bringing up an idea where we're including another force.
Yeah.
Okay? In this equation, the only force we're working with is what? No.
Gravity.
Gravity. Because this is the work done by gravity in both cases, right?
That's not realistic.
Okay? Well,
You're not gonna have a frictionless.
it's an
roller
idealized
coaster.
situation.
Okay, Brian.
Okay?
Theoretically, what would it be?
Okay. Well, let me finish explaining. Okay? So, right now in this system, it's an idealized, it's a perfect world scenario, right?
Yeah.
It's a 100% off the market roller coaster that has no friction. Not possible. Okay? Close to no friction is possible, but no friction is not. Okay? So, we're saying this roller coaster has absolutely no friction. That means there's no other forces acting on that roller coaster car besides what?
Gravity.
Gravity. Gravity is the only force acting on this roller coaster car.
Okay.
Okay? So this is what's called a closed system, meaning there's no outside forces.
That's
All right.
all we use.
Yep, that's what we're working with today. So now what you guys are talking about is if we added something, if we had brakes down here at the bottom which stopped the car, all right? Or if there's a lot of friction up here at the top that slowed the car down. What you guys are doing is you're adding an outside force. You're adding a force that wasn't the force that we stored the energy against. Okay? You're saying force we stored the energy against. When I moved the roller coaster car up here, we worked against
Gravity.
gravity, so I stored against
Gravity.
gravity. Okay? Does that make sense?
Yeah.
So that means gravity, in order for it to stay a closed system, gravity can be the only force acting on the roller coaster car. If some other force acts on the roller coaster car, be it friction, okay, be it brakes, okay, some magnetic force to increase the speed, because some roller coasters have that, okay, then we are not having a closed system. Now we're having what's called an open system, which means other forces are acting. All right. Now the open system is a real world scenario. All right.
This is all
But
fake.
closed system. No, it's not all fake. But the closed system is what we're going to start with so that we can look more in depth into the open system. Okay, does that make sense? Because when we go from open to closed, all you do is you just add some work to it.
Yeah.
Okay, it's the same equation with a little bit of work added in. Alright? So, the idea of open and closed system, we can use that to define our conservation of energy.
Okay.
Alright, so, conservation of energy.
Wow.
Nope. Conservation of energy, that's what COE stands for. So, Nan, Katrina, you guys are right when you said the COE was conservation of energy. Alright? Conservation of energy means that in a closed system, energy is never created or destroyed.
Never.
It only changes forms. Okay? So, in a closed system, okay? Now, for the roller coaster, a closed system means only gravity acts. Okay? So in this case, it's when we're only gravity acts. That's our closed system. Okay? So no friction, no anything else. Right? In a closed system, okay? In a closed system, energy is not created or destroyed. It only changes form. So any changes form, I'm going to draw a little PE, KE with a back and forth arrow. Because the forms the energy changes from is from potential to kinetic. Okay. Now some of you might be archers in here, might go bow hunting. Right? You're thinking, well, how does that apply? Okay. It applies the same way conservation energy still applies to a bow and arrow. Okay. When I pull back on a bowstring, I'm not storing gravitational potential energy. I'm storing elastic potential energy because I'm changing the shape of my bow. Okay, does that make sense? Then when my bow goes back to its normal shape, it propels the arrow. All right? So in that system, in order for energy to be conserved, the only force that can act is the force of your bow. Right? When gravity adds to that system, it actually changes the energy in the system. Okay? So it makes energy conservation a little more difficult. Okay? Same thing with a same thing with like if I bring two electrons right next to each other. The only type of energy in that system is electrical energy. That's the only energy being stored. And the only force I worked against to bring the electrons next to each other was the electric repulsion between the two. So once I release those electrons, all right, then they push each other apart. The stored potential energy by bringing them together turns into kinetic to push them apart. All right. Now, because of the interest of time, we're just going to focus on gravitational potential energy. So we're not going to worry so much yet. All right. Maybe when we get into the other chapters, we'll talk about elastic and electric potential. All right. So are there any questions about the idea of conservation of energy?
No.
Okay. So what conservation of energy tells us, what conservation of energy confirms, are these two equations right here. The energy we have to start equals the energy we have at the end. Does that make sense, guys?
It does.
Okay. Now, I want to look back at the roller coaster real quick, the one I drew up on the board. All right. So, where does the roller coaster have the most potential energy? At A. Good. Where is it the most kinetic energy? At B. All right. Now, at C,
It has a little both.
good. It has a little bit of both. All right. At C, we have both kinetic plus potential. And that kinetic plus potential is equal to our potential energy max we had at A. Okay? And it's also equal to our kinetic energy max we had at B. Okay? And these two energies, the energy at A equals the energy at B. Okay? The energy at B equals the energy at C. The car has the same total energy the whole way through. And that's what conservation energy tells us.
What if there was a loop?
Doesn't matter. Okay? As long as there's no outside forces like friction, air resistance, some type of magnetic force, any other force, as long as there's no outside forces acting, the only force acting is gravity, energy is conserved. Okay? Does that make sense, guys? Does that make sense?
Yeah.
Okay.
Yes, sir.
Michael, does that fit into your small height world? Yeah. Caleb, does that answer your questions about what friction or brakes occurred?
Yep.
Okay. All right, we'll get to that tomorrow.
Yeah, right.
Okay.
All right, any questions?
We done?
We done? We are never done.
Yeah, right. No, we're good.